Welcome to the massive open online course on Aspen Plus. This is the lecture 2 of this lecture series. In the introductory lecture, we have seen how Aspen Plus software can be used for process calculation, process engineering calculations, modeling, and simulation. In that lecture, we had taken an example of flash vaporization in which an equimolar fluid mixture of N-pentane and N-hexane were flash vaporized in a flash tank into two phases, namely vapor and liquid. First, we had done some hand calculation through textbook approach. We have gathered the data and relevant correlations from Perry's handbook. And after that, we have carried out the same calculation in Aspen Plus domain. And we have got comparable result. We have noticed that Aspen Plus software does the job rather fast and quite easily. And most importantly, we didn't have to write even a single code for that task. Today, we will go into the details of Aspen Plus and how it is used. I would like to tell an important information that Aspen Plus is available only for Windows operating system. Unfortunately, it is not available for Mac or for Linux or anything else. So whoever wants to use Aspen Plus, they have to have one Windows operating system. So this is a typical Windows desktop. And here you find the Aspen Plus icons. I have already loaded them in my machine, so you can find the Aspen Plus icon on the desktop. I have two versions. One is version V8.8 and the latest version V11. Now in this lecture, I shall follow version 11 because it is latest. But whoever has 8.8 version, they also will be benefited with this lecture series. So in order to work with Aspen Plus, first we have to click on the icon, double click on the icon. It will take some time. Yes, now it has opened. Here you may notice the topmost ribbon. Here you can just go one by one. The first one is what's new. So what's new, it gives the information about new features in this version of Aspen Plus. For an example, if you click on it, you will find what's new in Aspen Plus version 11. Now on the left side you can see the what's new features of Aspen Plus of previous version starting from 7.3, they are all given here. For instance, I have version 8.8 which I was using some time back. And between 8.8 and the present version, that is version 11, two more versions have come out and I have never used them. But I may be interested to know what these versions have as new. So I just click on what's new in Aspen version 9. It says it includes new features in the following areas like engineering enhancements, physical property enhancement, workflow usability enhancements, and its features. So if you want to see what are the enhancements in physical property, you can check over here. It says volume translation Peng-Robinson property model is now available. Now this is a thermodynamic model. Peng-Robinson model is quite known, but volume translation Peng-Robinson model may not be known to many people. Perhaps some scientist or researcher has published a journal paper on volume translation Peng-Robinson method or some advanced version of it, and they have added in Aspen Plus data bank. Further, the Pure 35 data bank has the following added compounds. For instance, sodium phenate, it was not there in earlier version. If I open version V8.8 in my machine, definitely I will not get this sodium phenate over there. It has been added in version V9. Similarly, version V10, we have similar kind of new features in the same areas. For instance, physical property enhancement, you just check. It has list of previously unannounced compounds added in Pure 32 or Pure 35. So just expand, you will find calcium hypochlorite, ammonium bicarbonate, dimethyl mercury. These were not there earlier, now it has been included. Similarly, version 11, it has quite a few new features, and all of them are explained below. Now, it might not be of very interesting at this moment for you because you are a beginner, but if you practice more and be expert in the version 11, then certainly whenever version 12 comes, you may be curious to know what are the new features in version 12 so that you can use them if it's required. Next one is examples. So it contains the example files delivered along with Aspen Plus software. So you do not have to download from anywhere or you do not have to purchase it separately. They come along with the software. Just let us see what are the things available. So examples with graphic user interface, you have batch modeling, biofuel, bulk chemical, carbon capture, energy analysis, fertilizers, etc. Now let us see what is there in carbon capture. Let us open. We find many things. Among them, this might be interesting. Amines E-NRTL-RK. Now those who are familiar with thermodynamic models, you know what NRTL means. It is non-random two-liquid model, and RK means Redlich-Kwong. Here E means electrolyte. Let us open. This basically is amine-based absorption of carbon dioxide. You might be aware that amine-based carbon dioxide absorption is a very well-established technique for CO2 sequestration. So here they have given the model for amine-based CO2 absorption where this thermodynamic model has been used but with different amines. So you have say monoethanolamine, MEA means monoethanolamine. It is diethanolamine. It is MDEA, PZ. PZ means piperazine, and so on. There is a mixture of piperazine and MDEA. So let us open this particular model, monoethanolamine. Just open it. Let us see what is there. Yes. So you can see a graphic user interface opens up where you will find heater, absorber, stripper. There is a heat exchanger, there is a pump, there is a mixture, and so on. It might be a flash. So this is a model where the amine-based absorption of CO2 is carried out. There is an absorption and desorption cycle that is shown over here. There is a recycle stream along with it. Now, if you want to see what are the components, you will find over here property set, component specification. So these are the components: monoethanolamine, water, carbon dioxide, carbon, hydrogen sulfide, and so on, nitrogen, oxygen, carbon monoxide. Many things are there. So these are the components. If you want to know what are the reactions happening inside, you can go to the reaction side. So these are the reactions going on over here. These are equilibrium based reaction, kinetic reaction, and these are the reaction stoichiometry. If you click on kinetic, you will find the very known Arrhenius equation. E is the activation energy, whose value is also given. Now, these are the informations given in this model. Now you can work with this model to learn how they have done it. For instance, if you work for a project where carbon dioxide sequestration is the main theme, then this kind of model will be of great help to you. The next one is the training. Actually, this whole portion is of resources. Training resources, model resources, events, announcements. Now, let us see what it is. This is called My Exchange. You can view your own downloads and browsing history. Now for that you have to register for it and you have to log in. Then only this can be stored in your name. Aspen Plus software comes with a lot of training material, documentation, models. One of the models that I have already shown to you, and other literatures and tools. For instance, it has over 30,000 literature, 6,200 documentation, 794 models, 135 training videos, 34 product updates, and event announcement. Everything is there. For instance, if you want to be curious about methanol, let us write methanol and search. Here you find 241 literatures available on methanol, 78 models that use methanol in it, 68 documentation, and 2 training videos. Now let us see what it is. The title is How Do I Model a System with Formaldehyde, Methanol and Water. All these search results, they have methanol, the keyword methanol in it. Now let us see what it is, and it is freely available. You don't have to pay anything for that. So it is developed by organization Aspen Tech. It is a free item. So if you want to see the article, just click on view article. So here it will show how do I model a system with formaldehyde, methanol and water. So this is a problem statement and this is a solution where they will tell you what kind of model has to be used for such modeling. It is UNIFAC liquid activity coefficient model. Okay? And this property package is applicable for the following range of condition. And they have taken it from the reference. These are the references. So from AICHE journal, 2 are from AICHE journal, and the third one from AICHE symposium series. So it's not from any arbitrary source. The source of their information is also reliable. Now suppose you want to check something about the carbon dioxide for CO2 sequestration. So just write carbon dioxide and search. So here you have how to fit CO2 partial pressure. How do you model liquid CO2 and so on. Okay. Suppose you want to see what is the training video available for CO2. Just click on it. So one training video is available on thermodynamics university module, regression of Henry's constant from vapor liquid equilibria. So if you view this article, or this is a video I think. So if you click on it, the video will open. There was an article associated. You can see the article, but you can also view the video. So
welcome to Aspen Plus V8.6 regression of Henry's constants from vapor liquid equilibrium data teaching module. For information on navigating the course, please refer to the navigation hints located above the slide. Click the next button on the right-hand corner to begin.
So not only you can watch the video, but there will be verbal description of the product also. So if you press next,
gas solubility is generally very small, up to a few percent. Henry's law is used to model vapor-liquid equilibrium of non-condensable gas, as opposed to Raoult's law, because the liquid vapor pressure of the non-condensable component required in Raoult's law does not exist above its critical temperature. Both carbonated drinks and diver sickness are common examples of Henry's law, in which the solubility of a given gas in a liquid is directly proportional to the partial pressure of the gas above the liquid.
So I close this video. Now there are a lot of such videos which are very helpful for a beginner as well as for an advanced user. Similarly, you have models, literature, tools and events. So if you click on events, you will find the upcoming events which are based on Aspen Plus. For instance, it is a Korea Operational Excellence Forum. They have some, I think it's an webinar, although I do not know Korean language, but it appears to be an webinar on November 19, 2020 from 9:30 to 12 p.m. November 12, there will be an APSC webinar on learn how Aspen HYSYS offers refiners streamlined workflows to update refinery planning. Similarly, December 2 there is an webinar, December 1 there is another webinar, and so on. So obviously if you are watching this video lecture after November and December, then these events are not of any use to you. However, this kind of event announcements always come up along with the Aspen Plus software, because the moment you connect to the internet, the Aspen Plus software connects to its database in Aspen Web, and from there it gathers the information to your desktop, and you can check the events and announcement. There are announcements also. You can click on the announcement and check. It is news about product releases and patches. So these are the announcements we have, the recent announcements. And whenever there is a new announcement which you have not seen since the last time you have opened this block, you will find a small red button and a number written within that red button. Actually it means, red button means a new event or a new announcement has come up. The number inside means how many such events or how many such announcements you have not seen, that it suggests you to see. So these are the announcements, like product lifecycle announcement for Aspen ACM model export. The second announcement is about Aspen Tech is pleased to announce that Aspen 1 2004 update 1 is now available. So these kind of announcements are also very useful for an Aspen user. So here you have certain blogs and discussions of user forum. There are millions of users of this software. They write blogs and they discuss about the problems they face. So if you are facing some problem, you can register in the blog and discussion. You can share your problem and somebody may answer. Some expert comments you can get, all sort of necessary help that you can expect from them. Now this ribbon actually is very helpful for beginners as well as the advanced user. Now we go back to our original starting page. So when you open the Aspen Plus software, the starting page will be like this. So you have already been updated about this ribbon. Now we shall talk about using the Aspen Plus. For that you have to open a new file or open an existing file. Now for opening an existing file, they will give you some hint of recent model, because you may be willing to start your work with a recent model that you were working a few minutes back or few hours back. We always try to work with some recent model first. So these are the recent model that I had worked with in past few days. For instance, this particular model we were working with just now. Okay, 5 minutes back we explored this model, the features and all. Now this flash, you might recall in the introductory lecture we had worked with the flash vaporization and I had showed you the example, and that file I have saved as flash. So flash dot the file extension. Now here you can see an interesting thing. The file that today we worked with, that has an extension BKP. Whereas the file that I worked with to show the introductory lecture, its extension is either APW or APWZ. That means all of them are Aspen Plus files, but they have different extensions. So before going into the details, let us discuss what are the types of Aspen Plus files that you will come across. So these are the file types and extensions of Aspen Plus. Now let us know what are the file types that we have. For that, let us try to open an Aspen Plus file. So click open. So it is asking for file name and Aspen Plus files. So you can see there are 1, 2, 3, 4, 5, 6 BKP, APW, APT, INP, APWZ and APM. So there are 6 types of files. Now let us see what those file types mean. So these are the file types and extensions that we have. We have template, user model, input, backup, document and compound. The first one is template file. Its extension is APT. Now it's a template with preferred units, property methods, etc. for repeated use. For instance, you are working in a team and your team is working for a particular project. So certainly in that project, you will have to operate on a particular process, and that process condition will be repeatedly used by your team members, everyone. And every time you try to model that particular system, then you do have to set the units, set the property methods and other environmental things. But instead, you can make a template, one template for all your team members. In that template, you fix the preferred units, whether you want to work with SI unit or the British unit. You can fix the property methods, whether you want to use Redley-Kwong, whether it is Peng-Robinson, whether it's an ideal system. And you fix a template file for everyone. So all your team members will begin from that template file so that the wheels should not be reinvented every time they work. The second one is user model. Most of the Aspen Plus unit operations that you will be using in a model, they are already in the software because most of them are very standard. For instance, your reactor, distillation column, pump, flash tank, heat exchanger, they're all standard unit operations. These models are standard and are available along with the Aspen Plus software. But you may have to work with certain equipment or unit operation which are not standard. You might be knowing the underlying equation, the mechanistic or the first principle equations that are governing the system, but Aspen Plus does not possess any kind of standardized block in its menu for that. So you have to develop some block for yourself and you call it a customized model. And that customized model will have all the underlying equation. You make it for yourself and your team members, and whoever wants to work with that particular equipment, he or she can bring it down from the menu and set it for its operation. So that kind of set or that kind of model can be kept under this user model whose extension will be .apm. The third type of model is input model .inp. Now, this model is a compact summary of input specification but no result. Now, you may be willing to work with a model, but you do not want to save the result. You may think that why to save the result unnecessarily? Whenever I want to know the result, I can rerun my software. It's just a few minutes job and I can get the result. So you want to save only the input specification of the process. So such kind of files can be named .inp file. So it contains only the input specification. The next type is backup file. So backup file, it not only contains input information but it contains the results also. So in input file, if you run this and get the result, and if you save it in .bkp file, then it is called the backup file. Now, all these files that I have talked about just now, they are ASCII coded. The next file that I am talking about is document file. Its extension is APW. It's a binary coded file. Now, I will tell you the difference between them. But this binary coded APW document file, it contains input information, results, as well as the convergence information. That means not only the final result, but what are the intermediate convergence that you had achieved while attaining that result. Each and every convergence information is also available in that file. Now, mostly you would be willing to send or share this APW file with your colleagues or your team members. Now, the question is, what is the difference between APW file and APWZ file? This APWZ file, the Z stands for zip. It's a zipped version. It's a compound file which is also binary. It's a compressed file of BKP, APW along with all its ancillary external files. Now, in recent versions of Aspen Plus, by default, they are saving the file as in the form of compound type. Earlier, this compound file was not existing. You had the choice of only BKP and APW files, these file options. Now, it is always better to save as backup file. Now, the question is, which type of file should be saved? Now, for that, we need to go deeper into these two types of files. For that, let us go to the location where I had saved my files. Now, this is the location where I have saved my files. You can see the folder flash. You will find two types of file. The first one is APW, the second one is BKP. So I have saved them in two versions. Now let us explore further. Here you type flash.apw. It's a binary coded file, but if you type BKP, it is ASCII coded. That means you can take a printout of this file and keep it somewhere as a printed document, so that in future if your storage gets corrupted, then you can recover your work. Although it will be a tedious job, but you will not lose anything. So it is always better to save it in BKP version rather than APW version. Aspen Plus by default it saves in APWZ file. From there you can extract BKP or APW later whenever you want. But you also have the option to save in these versions the way I have saved the flash BKP and flash APW files. Now there are various types of runs that can be conducted in Aspen Plus domain. These are the types of runs that you can do. The first one is property estimation. The second one is assay data analysis, then property analysis, data regression, and the fifth one is flow sheet. Now this flow sheet environment we have already seen when we worked on the flash vaporization problem. So it is used for standard process simulation, including sensitivity studies and optimization. Although the sensitivity studies and optimization we have not done in that exercise, but it can also be done. But this flow sheet run, it is dependent on other things, other type of runs. Whereas these four types of runs are all standalone. They are independent runs. Let us discuss one by one. The first one is property estimation. That is to estimate the property parameters. For instance, in the flash vaporization model we worked with N-pentane and N-hexane. If we recall, we had the inlet fluid, although equimolar, but they were having the temperature 140 degree Fahrenheit at 75 psia pressure, and inside the flash tank the temperature was 130 degree Fahrenheit and the pressure was 15 psia. Now obviously the physical property or thermodynamic property of a component like N-pentane and N-hexane, they depend upon the temperature. We all know Antoine's equation. It is for vapor pressure measurement. So we have measured vapor pressure, we have measured the specific heat, we have measured the enthalpy of vaporization in that flash vaporization exercise. So all of them were temperature dependent. So we had to measure these properties at 140 degree Fahrenheit as well as at 130 degree Fahrenheit. So how will we do it? Through property estimation. So not only that, you may have to work with density, thermal conductivity of the fluid and many other things, many other physical properties. So unless you estimate those properties, you cannot go forward. So property estimation is a very important thing. The second is assay data analysis. It is also standalone. It is to analyze petroleum assays and blends and generate pseudo components. Now in oil refineries, we work with crude oil. Now each crude oil type has its unique molecular and chemical characteristics. No two crude oil types are identical, and there are crucial differences in those crude oil quality. Now, extensive hydrocarbon analysis has to be done before sending the crude oil for further treatment in the refinery. So, we can do the analysis using Aspen Plus, and that is called the assay data analysis. So the next one is property analysis. This is also a standalone run. It is used to generate property tables. I mean, it is somewhat similar to property estimation, but in property estimation, we estimate only the data and we end over there. But in property analysis is one step further to it. So it generates the property tables, the PT envelope, residue curve maps, and other property reports. So it just analyzes and it can give you a comprehensive report on the property data of those components. The fourth one is data regression. This is also standalone. For an example, if you have a pure component which has not been there in the database of Aspen Plus, it's a new kind of component, then you can take the experimental results, you can have the density versus temperature or vapor pressure versus temperature data, and you can do the regression to find out the model parameters and you can set it. So that kind of regression also can be done through Aspen Plus. So it is to fit the physical property model parameters to measure pure component, this VLE, LLE and other mixture data. And certainly it can contain the property estimation and property analysis calculation. So the kind of calculation that they do, they use property estimation and property analysis as well. And finally, flow sheet that I have already discussed. Now overall, the Aspen Plus modeling and simulation procedure, it can be divided into these following steps: setup, units, components, properties, block, stream, and run. So these are the stepwise procedure for Aspen Plus simulation. The first two things are not mandatory, but they are advised. And the last 5 are mandatory for a successful operation. Setup actually defines the title, description, and purpose of the job. For instance, if we go back to our Flash model, so this is flash.apw that we have developed in the introductory lecture. Here I didn't give any title, but still it worked. But I should have given a title. Let us give a title. You can write it as a flash vaporization example. The next one is description. Description, you can again write this example model was created for demonstration purpose of flash vaporization operation. The next one is accounting. Again, your company may give a username to you for all your work. You can write that username or account number. The project that you are working with, That project ID also can be written over here, and the project name in which this software is used, that project name also you can write. Now the next one is units. That is unit of measurement, SI or English, for input and output data. Here also, in the introductory lecture, the flash vaporization example, we worked with English unit. Okay, so here English unit was given, but you can change the unit over here. Instead of English unit, you can write metric, or metric with C bar. Temperature is in centigrade, pressure is in bar, or purely SI unit. So everything will be in kg, kilomole, Kelvin, etc. Or else, if you are not happy with these units, you can create your own unit. Here if you click, you will get this. You can say new, and you can write it as my unit set. Okay, there is a character limit. You cannot use more than 8 characters. So my units, that's all. So here it is asking for defining your unit. So you copy from SI unit and then change as per your requirement. For an example, you may say that I will put the mass flow rate in, not in kg per second, but I will give it in pounds per hour. Whereas moles, I want to keep it in, it is kilomole per day or per week. Although it is word, but you can change your units accordingly. Temperature, you may say that I want to give it in Rankine. Similarly, heat, you may say that I want it into megajoule, whereas heat flux, I want to give it in gigacalories per hour m. Now you can mix and match depending upon your wish. You can mix and match and create your own unit set. And once you set it, then you can choose my units rather than your SI unit. Okay. So accordingly you will get all your results. So these are all globally set units. Okay. That doesn't mean that while working with the problem you do not have the opportunity to change the unit. You do have the opportunity to change the unit, but if you change it globally once for all, then you will have less requirement to change the unit inside the simulation. Okay. But they are not very much required. So these two things you can always skip. You can use the default one, whatever it is there. But these are very important. First is the component and properties. The next one is blocks and streams. The third one is run. That is the run that you want to do. Now obviously, if you want to do property estimation, then you do not need this block and streams. They will come only for flowsheet run. Now the components are chemical components to work with. For instance, we worked with N-pentane and N-hexane for our flash vaporization operation. And then the properties, physical and thermodynamic property methods and model. In our flash vaporization exercise we have taken an ideal system, but in reality some kind of non-ideality will always come. So based on the components and the system, you will have to choose your physical and thermodynamic property methods and models. So you have to know what kind of models that you will use. So there are help files for property methods that I will explain later. And finally, the blocks and streams. You have already seen a small glimpse of how the models and streams were set in the flash vaporization model. There were a model library at the bottom, and we had to choose the flash tank, and we connected the streams in this fashion. This stream we named as feed, this feed we named as vapor, and this feed we named as liquid. So choosing unit operations blocks for the simulation environment and connecting the feed and energy streams to the block. Now on that day we only showed the feed stream, we have not shown the energy stream, but I'll definitely show you an energy stream, how it is added for a particular example at certain time in future. And finally, run the simulation and analysis of result. So this is the complete modeling and simulation procedure. Now to summarize, we have two important environments that we have to set. One is component environment, the properties environment, and the second one is simulation environment. These are the two items that we have to take care: properties environment and simulation environment. Next one is setting the environment. What are the items that we have to set in properties environment? We have to set components, physical property, thermodynamic property, equilibrium model, and gas model. Whereas in simulation environment, we have to add flow sheet which contains the blocks and streams. Streams will have both mass and energy. Now let us get introduced to various features that are available on the Aspen Plus simulation window. At the top, you have menu bar, file, home, economics, batch, dynamics, plant data, etc. We will learn one by one later, but these are the menu bar where you will get various features of Aspen Plus. Then at the corner, you may find one question mark sign. This is help button. So if you click here, you will get help, ready help. For instance, if you want to know about some thermodynamic model, say Peng-Robinson, so you write Peng-Robinson, then it will search, and there are 59 results. Aspen Plus has various documents where Peng-Robinson has been mentioned. This is the original Peng-Robinson equation of state. This is volume translated Peng-Robinson method that we just talked about half an hour back, and various other variation of Peng-Robinson equation. So you can get lot of information over here. So this is the equation for Peng-Robinson model. This obviously the main flow sheet where you can build your model. You can get models from the model palette. This is model palette. Here you have mixers and splitters, separators, exchanger, column, reactor, pressure changers, etc. So you can just bring in the model that you want in your system. And this is the material stream, and you also have heat and work stream. Heat means energy stream. So it will not carry any material, it will carry energy. Then obviously this is the scroll bar. These two are scroll bars, and this is the select mode. If you select like this, then the whole part is selected, or you can select only this much, then only the block is selected. And then you can copy, you can cut, you can paste elsewhere. And this is the prompt area. Prompt area means here everything that happens over here will be prompted. For instance, suppose you go to the stream. So this is the stream, it is feed stream. You change the input of the stream. So instead of 140, you say 150. Okay. The moment you change, it will be prompted input changed. Okay. Now, when you run, this is the run button. So when you run, it will show results available. Now it did it too fast, but between input changed and results available, there was a very short period of time. You might have seen processing. So they are processing the calculation. So that message also appeared, but for a very brief period of time. So ultimately, the results available right now. And the last one is the next button. If you press next, then the Aspen Plus will take you to the point where the next input is required. It will go in series until and unless all the inputs are given and the model is ready for further simulation. So it is always better to press next whenever you are building a new model in Aspen Plus. Now we will learn about various symbols which are used as status indicator for Aspen Plus simulation. For example, suppose in input, you will find that there is a small blue circle within which there is a white tick. This always means that the input is complete, or if it is there in results, then results are available. Either it means results are available or it means the inputs are complete. For instance, suppose these are the minimum input information, those are required for the simulation to go forward. Now, if I delete this information, then it will show a circle with half red and half white. This particular symbol indicates that the input is incomplete. We just hover around it, it will show required input incomplete. That means the simulation cannot go forward with this. So if you do not want to give pressure you can give vapor fraction. So you can say vapor fraction anything between 0 to 1. But information has to be given. So if you give vapor fraction, say, if you say our input contains 50% vapor and 50% liquid, then vapor fraction, if you give 0.5, again you will find blue tick. I mean white tick within blue circle. That means input is complete. Now you might see that you have got a new type of symbols that have appeared over here. This symbol will occur if the input has changed. So here the result summary exists, but input has changed. So the results that you will get over here, that is not reflecting the result of the simulation for this set of input, because the input has changed. So when you run it, if you run, this is the run the simulation button. So if you run, again you will find all of them with white tick within blue circle. So that input change option has vanished. Again, if you change it to say 140 to 150, this symbol arrives again. And there is another type of symbol which is red colored cross mark. And that means the results are available, but there is a calculation error in it. I will change the simulation a bit. For instance, let us change the simulation condition a bit. Let us say our pressure is 1 atmosphere, 1.1 atmosphere, and our flow rate is 1 kilomole per hour. And then we want actually this particular vapor to, let us change the name so that we can understand it better. Let us go to the main flow sheet. We rename it as feed. This we rename it as vapor, and finally this we rename it as liquid. Then we'll learn it better. Now feed we have reformatted. Now feed, now we have changed the feed condition. Now vapor condition we may not give, because vapor condition is not required. It will calculate of its own. But let us demand the Aspen Plus to calculate a condition through which we will obtain the vapor at 150 degree Fahrenheit with pressure 1 atmosphere, and we want the entire vapor, entire content of the feed to go to vapor, and also let us add another component, water, in it. So for that we need to go to properties. Here let us add water. And then let us run the property estimate. Okay, go back to simulation. Here in feed, let us change it to 0.4, 0.4 and give 0.2 to water. And we want the vapor to have the same composition. Right? So let us go to block, and we will say that block temperature should be 200 Fahrenheit and there is no heat duty, zero heat duty. Okay. Now let us see what happens. So let us understand what are the changes that we have made. First, we have added a new component, water, and then we are saying that my feed contains 40% pentane, 40% hexane and 20% water. The total mole flow rate is 1 kilomole per hour. The temperature 140 degree Fahrenheit and pressure is higher than atmospheric pressure, so it is 1 atmosphere. So that enters in the block flash where the temperature is higher, it is 200 Fahrenheit, and we are not giving any heat duty. The heat duty is 0. And then we are going to vapor phase. We are expecting the entire fluid content will come out as vapor at the same mole fraction. Obviously, if everything comes here, then mole fraction will be identical. But we want the temperature to go up as well as the pressure should be reduced. So think of the condition. My feed is at lower temperature, higher pressure. Vapor is at higher temperature, lower pressure. In between, it goes through a block flash where the block is maintained at 200 degree Fahrenheit with zero heat duty. Now, this kind of situation is practically impossible. So now, if we say next, then it will say the required input is complete. Run the simulation now. We will say yes, you run the simulation. Immediately, it will give some error message. So what it will say? It says results available but with error. Okay, so this is the red cross mark. Red button with a white cross inside. This means results available but with error. Okay, so it is severe error actually. So these are the problems that has been stated over here. Simulation calculations complete but with severe error. So these are the various status indicators and their symbols. So we end our lecture at this point. We'll continue in the next lecture. Thank you.